Hopefully yeah, you can see my screen. So let's get into it. So part one of part one just tells you to get a coin, a pencil, and a paper, and you're going to flip a coin 100 times and just tally down every time it's heads or tails. Okay. I've had folks do this using a coin flipping app. That's perfectly fine. If you know how to make Excel do random numbers for you, that's fine too. But find a coin is probably the easiest way. And then it says calculate the chi-square using the following equation, show your work in panel 1, record the degrees of freedom in data table 2, use the chi-square distribution table to determine the range of the p-value, record the p-value, in data table 2, record whether your p-value was greater than or less than 0.05, quack, quack, quack. I'm going to show you, we're going to go through a couple of examples of how to run these today in lab, because it's a really intimidating looking formula. Like if you haven't taken math recently, this looks terrible. But like I said, we're going to run through it at least a couple of times today and demystify it a little bit, and hopefully it'll be a little less awful by the time we're done today. The first thing I'd like to point out to you is this is a chi-square. It looks like a little x squared. It is the Greek letter chi. And the thing I'd like to let you know is, even though this is chi-square, you are never taking a square root. It seems counterintuitive, but you are not taking a square root at all. Okay, do not attempt it. It will make your answer wrong every time. Okay, do not take a square root. This is just a symbol. You can think of this as the letter X, the letter Y. You can think of this as a question mark if you like. It doesn't matter. I'll say it again. Do not take a square root. If we continue looking at this here, we have this another awful, horrible looking Greek letter. It's like capital E looking thing here. This is a sigma, and this just means add everything up. I'm going to tell you exactly what that means in the context of this equation in just a few minutes. And then we have the actual formula here where you're going to plug in numbers. You have your observed value, you have your expected value, you square that, and then you divide by your expected. And again, we're going to go through it. I'll show you exactly what's happening with this. So I ran the simulation that you're supposed to run, and I want you to run your own. If you have these exact numbers, I know you're probably making them up, but I flipped a coin 100 times. I got 42 heads and I got 58 tails. So let me ask you guys this. If you flip a coin 100 times, what's your expectation? What do you expect to have happen if you flip a coin 100 times? Say it out loud, put it in the chat. What do you expect? Flip a coin 100 times. (50-50), 50 heads, 50 tails. And Caitlin said something interesting, and that's you either get heads or tails. That is true. That is one of the definitions of a fair coin, is it kind of can't land on its side or be halfway in between or anything like that. So yes, heads or tails, 50-50. You guys are totally right. And then I guess the other question that I would ask is, why would you run a chi-square test on a coin? Does anyone know that? This is a harder question. But why might we want to do like statistics on a coin? What's the point of this? Well, I mean, the point of this specifically is to practice chi-square, but what's the point of why would someone ever run a chi-square test, much less on a coin? So the reason that you do a chi-square is that you're doing it to determine whether or not your actual data, your observed values, are statistically different from your expected values. And so in this case, if we were doing a chi-square for a coin, what that would mean is we're checking to see if this is a fair coin. We're checking to see, is this coin weighted in some way? Has this coin been manipulated to land on heads most of the time? All right. That's the point of a chi-square. And again, it's kind of a silly example because it's a coin. The coins you're ever going to run across are fair. But that's the point of this. And this has connections to the field of genetics that people use. And we're able to figure out some more interesting things beyond just, oh, is this coin cool or not? So anyway, I ran this trial and I got 42 heads and 58 tails. We said that our expected values, or you all told me that our expected values were 50 tails and 50 heads. Okay, so let's start running our chi-square calculation. So here we have our observed values. Where did these numbers come from? These observed values. Where did I get those? 58 heads, 42 tails, or 58 tails, 42 heads, I should say. Where did those come from? Right, exactly. I flipped the coin a bunch of times. These are my actual empirically collected data. And these are my expected values that you guys brilliantly told me earlier. So we're going to run this. We're going to start with tails, okay? And we're only concerned with the stuff that's to the right of this sigma. We're only concerned with the stuff that's written in English plus the square. Okay, so our observed minus expected, our observed value is 58. I flipped 58 tails. And our expected value is 50. Okay, the math so far hopefully isn't too horrendous, right? 58 minus 50 happens to be 8. Then we need to square that value and divide it by our expected value. So everyone in here, I'm sure, can do this first part at least. Okay, just observed minus expected, then you square it. And when I say square, I mean multiply that number by itself. And so 8 squared is 64. And then you just divide that by your expected. Is this okay? Is everybody all right so far? If you have a question and you're a little shy, you can just DM me. I won't call you out publicly. I'll just answer your question. But is everybody okay so far? These slides have already been posted. Let me see where I posted them. They're in this week. Let's see, they are called Genetics Lab Meeting Slides. All right, let's trudge on. Observed minus expected, 58 minus 50, we get 8. Then we square that number, which gives us 64, and we divide by our expected. Okay, 64 divided by 50 is 1.28. Okay, we're almost done with this first example, but let's put that information off to the side. And now we're going to run the same calculation for heads. What's our observed value for heads? And what's our expected value for heads? Somebody give these to me. What are our observed and expected values for heads? Observed is 42, and our expected, you probably are all rolling your eyes, it's 50. Yes, thank you. Okay, so our observed is 42, our expected is 50. We're going to take 42 minus 50. This is actually a negative 8, which, by the way, doesn't matter because we're going to square it. Take our observed minus our expected, we square it. That gives us 64. Then we divide by our expected. and that gives us 1.28. Okay, so now we have these two different values. Are we done? Or what's the next step, I guess? What do we do now? They want to take a swing for the fences? That's exactly right. You apply sigma, which is a great way of saying that. But I think a probably more intuitive way of saying it is now we just add them up. So we did observed minus expected squared divided by expected for tails. Now we did it for heads. And now we have to deal with this awful Greek letter here. But all we do to deal with it is we just add these two things together. Okay, we got 1.28 for heads. We got 1.28 for tails. That gives us a value of 2.56. Still not done. Sorry, I know we just did all that awful math. The next thing we have to do is consult our table and figure out our degrees of freedom. Without getting too statistical or philosophical, degrees of freedom just means the number of possible outcomes minus 1. And it's just a math thing. For our purposes, just memorize it. Okay, you don't have to memorize this formula, this chi-square formula. If I ask you about it on an exam, I'll give you the formula. I'm not interested in you memorizing this. But how do we figure out what our degrees of freedom is? So I said number of possible outcomes minus 1. If you have a regular coin, how many outcomes are there? How many possible things can happen? Yes, exactly right, Edgar. It's degrees of freedom in this case is 2 minus 1. So why is it 2? Where did the 2 come from? Right, exactly. There's only 2 things that can happen when you flip a coin. And this isn't including like, oh, it could roll across the floor and your dog could eat it or something like that. There's only 2 things that should be able to happen, heads or tails. So degrees of freedom is the number of possible outcomes minus 1. Degrees of freedom in this case is 1. If we were picking a random number, 1 through 10, or actually, let's do it like this. We're going to be talking about dice in a minute. If you roll a single die has 6 sides. How many possible outcomes are there for a single die? There are 6 different outcomes. So what's the degrees of freedom for a die? That's exactly right. It's 5. Okay. And don't worry if you didn't catch that all just now. We're going to do it again in just a minute. But we've calculated our chi-square value for my particular set of coin flips. We've calculated our degrees of freedom, which is 2, or which is 1, I should say. And now we need to consult our value, our p-value table. Let me try that again. Now we need to consult our p-value table. So what you do is you look for your degrees of freedom, which is this first column here. We only have 1, so we're looking for values within here. And the lab specifies that we're using a 0.05. So we're looking for values here. So our number happens to be 3.84. All right, now you'll notice that 2.56 is smaller than 3.84. Okay, so our results were not significant. What does that mean? Like, we've done some math, we've done some talking about math terms, we've consulted this weird table thing. What does it mean that the numbers that we calculated are less than the numbers on this chart? What does that mean? I can never tell if people are typing or oh, good. Not quite. Somebody said our results weren't entirely representative. That's not quite it. Our results probably were, they definitely were representative of that coin at least. So let me ask you this. When you pick up a random quarter and you start flipping it, what are your assumptions? By assumptions, I mean, if you were to flip that coin a million times, you would expect it to be 50% heads and 50% tails. Expected more than our outcome displayed. That's not quite right. What this means is that we don't have enough data to show, or our results are not different enough from our expectation to show that this coin is unfair. I'll say that again. So what this means is that our results, our observed values, were not different enough from our expected values to show that this coin was unfair. So what if we had gotten like different numbers, or like what if I had flipped and gotten 90 heads and 10 tails? What would our chi-square value look like? Would our chi-square value be really big? Would it be really small? Bring back our formula. So if instead of 58 and 42, I had got 90 and 10, what would our chi-square value look like? We could just do it here. I got a bunch of crap. So let's say we have our heads, we have our tails, we have our expected values. Expected values, we have our observed values. So we're flipping a coin again 100 times. You already told me that our expected values were 50 and 50, but let's say we got 90 heads and we got 10 tails. Okay, our formula is observed minus expected squared divided by expected. Okay, so this one's for heads, this one's for tails. So 90 minus 50 is 40. 40 squared is 1600. 1600 divided by 50 is going to give us 32. 90 minus 10 is 80. 80 squared is 6400. 6400 divided by 50 is 128. So our values are huge, right? And maybe I'm not getting this across well, but if your observed values are very, very different from your expected values, your chi-square number is really big. Okay, and the further away your observed values get from your expected values, the bigger and bigger your chi-square value becomes. So let's look at our table. You know, this is our, in this case, our chi-square value is 160. I think that's right. It's really big. It's like 160. So let's go back to share my screen again. Let's go back to our table. And yeah, 160 is definitely way bigger than this, right? May have lost some of you. The point here being, because our chi-square value is smaller than that number, we have a fair coin. Statistically, we have a fair coin. Okay, is that all right? Is everyone following along at least somewhat? Does anybody need me to go back? And again, we're going to do this again. So the other thing that I'd like to point out here is that what does a 95% confidence mean? Oh yeah, so how did we pick the columns that we did? Okay, so the degrees of freedom is the number of possible outcomes minus one. So in this case, it's either heads or it's tails. And so 2 minus 1 gives us 1 degree of freedom. And now here's the nuanced part, and that's selecting your confidence level. Now, the reason we picked 95% or 0.05, which I'll point out that 95% is the same thing as 0.05, or a 5% chance of this being accidentally different. But the lab told you to pick 0.05. So degrees of freedom we calculated, and then the lab told you which one to pick in terms of percentages. But the thing I'd like to point out is that 95% confidence sounds great, but that means that 1 out of 20 will just by chance deviate from this. So theoretically, if you ran this experiment 20 times, one time your data would tell you that you have an unfair coin. Which, you know, so I have like 120 students. So 6 people should tell me that they have a coin that's not fair. Which is kind of a problem. If you're reporting a 95%, you know, if you're saying, well, we ran this test at a 95% confidence level, it's like, well, you probably have good stuff, but 1 out of 20 is not, you know, you're not like calling the newspaper, not that anyone would call the newspaper, but you're not calling the news if a 1 out of 20 shot happens. Anyway, let's do this again. Let's do this a slightly more complicated example. We will run this for some die, and it tells you here are the instructions here. You're going to roll a die 60 times. So a die has 6 sides. If I roll it 60 times, how often do I expect to get each number? So how often do I expect to get 1? How often do I expect to get 2, 3, 4, 5, and 6 if I roll it 60 times? Right, you expect to see each number 10 times. This is our expected value here, okay? I'm expecting to get 1 10 times, 2 10 times, 3 10 times, 4 10 times, 5 10 times, 6 10 times, okay? So I actually did this experiment. Here are the results that I got. So again, our expected values just come from us being naive about this particular die. Oh, I've never seen this one before. I will assume that it's fair. I actually roll it 60 times. Here are the data that I get. Okay, here's our formula again. Let's go ahead and stick that up there. So the first thing we're going to do is calculate our observed minus our expected value for each of these. So I'm going to take 15 minus 10, 8 minus 10, 7 minus 10, 12 minus 10, 6 minus 10, 12 minus 10. Does everyone see what's about to happen? For each of these things, we're going to take our observed values and subtract our expected values. And there we go. These are the numbers that I got. 15 minus 10 is 5, 8 minus 10 is -2, 7 minus 10 is -3, 12 minus 10 is 2, 6 minus 10 is -4, 12 minus 10 is 2. And I'd also like to point out here that because we're going to square these things, that the order doesn't actually matter. This could have just as easily been expected minus observed, because we're going to square them ultimately. And so, you know, if you got -5, -5 times -5 equals 25. 5 times 5 equals 25. It doesn't matter if it's positive or negative. I would suggest just doing the formula correctly, but if you do happen to mess it up, it'll be fine. Okay, we've got our observed values, we've subtracted our expected values. Now we're going to square those. 5 squared is 25, -2 squared is 4, -3 squared is 9, 2 squared is 4, -4 squared is 16, 2 squared is 4. And I'll also, I'd like to urge some caution, especially for folks that haven't taken a math class in a while. Sometimes on some calculators, if you put -4 squared, it's going to give you -16, which is wrong. Okay, just be cautious of that. All right. All right. We've got our observed minus expected. Now we have squared this value. What do we do next? Somebody let me know in the chat. What do we do next? That's exactly right. Now we're just going to divide by our expected value. So 25 divided by 10, 4 divided by 10, 9 divided by 10, 4 divided by 10, 16 divided by 10, 4 divided by 10. Those numbers give us 2.5, 0.4, 0.9, 0.41, 0.6, and 0.4. Okay, got this calculation done. What is the next step in determining our chi-square value? There's a hint right there. What do we do next? That's exactly right. We add all of these numbers together and we get like 5.81. Cool. Are we done? We just have this random number. Unfortunately, we are not quite done. There's a couple of more steps. I guess the first thing, or the next thing I'd ask you is, what is it? What are the degrees of freedom for this example? What are our degrees of freedom? Five, that's exactly right. How did you come to this conclusion that our degrees of freedom is 5? Seems kind of random. You just pick a point, just pick a number. How did we arrive here? Were you just paying attention earlier? That's a great explanation. There are 6 possible outcomes. We subtract 1, that gives us 5 degrees of freedom. I'm a bit of a huge nerd, and I used to play a game called Dungeons and Dragons. And in Dungeons and Dragons, you have a bunch of different kinds of die. But one of those is a 20-sided die. What would our degrees of freedom be for a 20-sided die? Exactly. Okay, cool. So there are 20 possible outcomes, 20 minus 1, degrees of freedom for a 20-sided die is 19. And again, this is just, I don't necessarily need you to understand this mathematically or philosophically or statistically. Degrees of freedom for our purposes can just be something that you memorize how to do and then you find it on the chart, okay? You take other classes, you take statistics, you can figure out a little bit more about what it really means. But for us, how many things can happen? Subtract 1, boom, degrees of freedom, look it up on the chart. All right, let's trudge along with this problem here. We summed all of those numbers up. We got 5.81. Where do we go on the chart here? And this is kind of the same question I've been asking, but where do we go on this furthest left? Like how far down do we go to look for numbers? Right, exactly. You go down to the 5. Work, computer. You go down to the 5 and you go to 0.05 because again, the lab tells you to look there. And this might seem kind of random, and it is. It is up to the experimenter. It's up to the person doing the experiment to determine how confident they are in their results. 95% is very common though, so we'll go 95% confidence. All right, so 5.81 is less than 11.07. What does that mean? We've done all of these numbers, we've run this calculation, we figured out degrees of freedom, we even did a Greek letter or two. What does it mean now that we've done it all? What does it all mean? Someone DM'd me and said that the die is fair for the most part. I agree. I wouldn't say for the most part. I would just say that the die is fair. According to the statistical test that we ran, this is a fair die. Okay. Our numbers are not big enough, so we accept the null hypothesis, as it's called. The null hypothesis. And so for us, again, if you walk into a room and you pick up a regular die, you assume that it's fair. That is your null hypothesis. In order to reject the null hypothesis, as you'll hear often in statistics, you need proof. You need some kind of big data, or you need big numbers to prove, oh, hey, this person actually has carved this die in a particular way so it lands on 6 most of the time, or 1 most of the time, or whatever the number is. Okay. So because our chi-square value is small, we fail to reject, or we accept the null hypothesis. These are fair die. So I'm going to go into, I want to do a quick review for the quiz for everybody. But again, I just want you to make sure that you write down somewhere, get yourself a 100-watt heating bulb. We're going to need it for a couple of labs. I think I have 3 of these in my office. And so if you absolutely can't find one, let me know and I might be able to get you one, but I have a lot of students. So I definitely don't have one for everybody, all right? So I hate to, I said this morning too, I hate to endorse something like Amazon, but you should be able to find these things on Amazon. Just get yourself one so we can get the labs done, okay? So the quiz on Wednesday. So again, if you are a person that waits until Saturday or Sunday to do these, fine, I'm cool with that. Just make sure that you are reading the lab itself before Wednesday, because you'll be able to fill in some of these pieces. And let me start this by asking, does anybody know what an allele is? Does anyone know what, like if we're talking about alleles, what am I talking about? What is an allele? Different form of a gene is a great way of phrasing that. A capital letter to indicate a dominant trait and a lowercase letter to indicate a recessive one. That's also a good definition. So the example I used this morning, I'll just go ahead and continue using it, is I have blue eyes. Blue eyes are a recessive trait. And so I got, I got one allele from my mom, I got one allele from my dad, and I happen to have this genotype with my two little b alleles. If you're totally lost, please check out the lectures for this week. But I know my alleles. And I know my alleles from my phenotype, by the way. So let's talk about Punnett squares for a second. My mom has blue eyes. So what are her alleles? Does anyone know what my mom's alleles are? She has blue eyes too. Yes, exactly. So my mom's alleles, she is also little b, little b. Okay. Make ourselves a little Punnett square here. Okay. So both my mom and I are what is called homozygous recessive. What does homozygous mean? Is anybody up on the reading, or what does homozygous mean? Having two copies of the same gene. Homo meaning same, zygous referring to our alleles in this case. So we are both homozygous recessive. Now my dad has brown eyes. Does anyone know what his alleles are? What's my dad's genotype? I'll have that up here. Folks are saying heterozygous or big B, little b. Now, how do you know my dad is not homozygous dominant? How do we know my dad's not homozygous dominant? How do we know my dad's not big B, big B? That's exactly right. So let's make the Punnett square if my dad was homozygous dominant. So how do we fill this Punnett square in? Have you guys done Punnett squares lately? How do we do this? What goes in this square, this top left square? That's right, it's a big B and a little b. Where did the big B come from? The big B came from this B right here. This B gets brought down. In fact, we'll bring it all the way down. This big B goes down here too. What goes with this big B? That's right, a little b. So this big B goes in both of these. These little b's go across. All right, so if my dad was homozygous dominant, all of my parents' kids would be heterozygous. So if this were the case, what color would all of my parents' kids have? Weird question. What color eyes would this couple's kids have? They would all have brown eyes. And again, that's because this is this is called a purely dominant or purely recessive trait. And so if you have one capital letter, you wind up having that characteristic. And so if my dad was homozygous dominant, all of their kids would have brown eyes. I'm fairly confident that my dad is who he says he is. So we're going to assume my dad is heterozygous. And let's do another Punnett square. What goes in this top left corner now? We have a big B here. Again, this big B comes from the top. This little b comes from over here. The same thing goes down here. This big B is coming from up here. This little b is coming from the left. What's going to go here in the top right now? That's right. So one little b comes from up top. The other little b comes from over here. We're also going to put little b down here. Okay. One little b comes from the top. One little b comes from the left. And so this is what this particular cross for my parents looks like. Half their kids should have brown eyes, half their kids should have blue eyes, which happens to be the case. But this is how the chi-square comes into genetics. Let's say, for instance, this couple, let's say my parents had 100 kids, which is weird to say and weird to think about. How many do we expect to have brown eyes, and how many do we expect to have blue eyes? What is our expectation? They had however many kids. 50-50, right? Half and half. Half should have brown eyes, half should have blue eyes, or some number close to it. Okay. So do check out the lab. Okay. These are genotypes. The actual characteristics that these people have are their phenotypes. So let's see. I'm going to give you another example. It's out of the way. There we go. Clear our drawings. I'm going to give you another trait. This is a trait called polydactyly, and we're going to use a letter H. Okay, this is a trait called polydactyly. Here is this is the dominant form. This is the recessive form. Has anyone heard of polydactyly before, by the way? Polydactyly. No, okay. It can be for animals, certainly, but this is also in humans. Polydactyly means that you have 6 fingers on your hands, or it could mean you have 6 toes on either foot. And polydactyly is an interesting one because polydactyly is actually dominant. If you have a big H, you have polydactyly. So let's go ahead and make a cross of, what do we call this genotype, by the way? What do we call this one? Is it heterozygous? Is it homozygous dominant? Is it homozygous recessive? Which is this one right here? Yeah, it's heterozygous. So let's go ahead and we're going to mix up 2 heterozygous folks. With both of these people have 6 fingers on their hands. So what goes in this upper left-hand box? What goes here? That's right. And what do we call that? What do we call big H, big H? Exactly. This is homozygous dominant. Now, what goes in this box here? That's right. We're going to grab the big H from the top and bring it down. We're going to grab the little h from the side and bring it over. So this is big H, little h. Big H. That's a big H, I promise. And what goes over here? A big H, little h. What goes in the bottom corner here? That's right, little h, little h. So in terms of our genotypes, we have, as you may see in the lab, a 1 to 1 ratio. What on earth does that mean? What do I mean by 1 to 2 to 1? Well, we have 1 homozygous dominant. We have got 2 heterozygous. And we have 1, 2 right here. Probably shouldn't use red, but that's okay. And then we have 1 homozygous recessive. So we have a 1 to 2 to 1 genotypic ratio. This is different from our phenotypes, right? What's a phenotype? For those of us who've already seen this, what's a phenotype? A phenotype is our observable characteristic. So in this case, this is actually a 3 to 1 ratio. This is 3 to 1. Why is it 3 to 1 instead of 1 to 2 to 1? Where did I get 3 from? Just making stuff up? Where did I get 3? That's exactly right, because 3 of these offspring, and you said 3 people, which is you're on the right track here, but 3 of the 4 offspring in this case have an extra finger. Okay, so our ratio is 3 to 1. So again, genotype is just the genes. I said again, I hadn't said this yet, but genotype is just the genes. It's what are your alleles? What do your little letters look like? Phenotype is your actual characteristics. Okay, so we have a genotypic ratio of 1 to 2 to 1, but we have a phenotypic ratio of 3 to 1. How is that? Is everyone sufficiently confused? Questions? Let me do this. I'm still going to ask for questions. I'm going to go ahead and stop the recording.